Can you see my screen? My network is actually acting up. All right. So let's quickly start. We have a hard stop for 9:30. Yeah. The ISA event is coming up by 10, and then I have an event between 9:30 and 10:15. Just a short meeting. So we have a hard stop 9:30. So, but we can still get some things done before then. So thanks once again for for those that have been joining the call regularly. We've been going through this module, right? And what we are doing today, we have just about four modules: M7, M8, M9, and M10, which is like a capstone where you design a complete control system from scratch. You choose your process, you set parameters, you configure alarms, you tune your PID, you run the simulation, and you receive an automated performance score. So today we are focusing on PID control, right? And to get the best of this, I hope for those that have been attending, you paid attention to at least the last 3 lessons from M4, M5, and M6. Right, those were the lessons that built the background and the right foundation for understanding M7. Because as these terms, as simple as these terms are, the PV, the SP, and the MV, and the relationship between them, they are very vital to understanding M7, right? The PID control. And the process dynamics and time constants, that is the explanation of the physics behind each process rather, the physics and mathematics, the natural behavior of each process. We explained it in the last M6, right? Last module. So, and then of course, feedback thinking, the error correction over time. This is very key. Error correction is not an instant thing. You do it over time. There is always a time T, that lapse, right, for you to achieve your error correction. And I mentioned that this is where we begin to separate the men from the boys, right? Or the boys from the men, whichever one applies, in managing, whether designing or managing control systems, and especially writing efficient PLC programs. Because if you've been writing PLC programs and you've never designed timing, you've not looked into the timing of a PLC program, it's just like someone claiming to be an embedded systems engineer and all he or she can do is Arduino, just work on Arduino and Arduino Sketch. You make some projects and they will work, but when push comes to shove, right, you won't be able to do certain things. Like I always say, engineering is the intersection of quality, performance, and safety, right? The intersection of those three, that is engineering. You can build something and it functions, but does it have quality in the sense that how long will it last? Can it function in the kind of environment where it is needed? Right? So you need to balance performance, safety, and functionality. And that is where the true genius of engineering comes from. Right. So, saying that, let's get into quickly into this. Again, this is Insight Sim. It's a um, simulator. It's a training simulator, which myself and my team developed. We're presently testing it. We're presently testing it. It should be available the next probably in the next 2 weeks, or maybe 10 to 12 days. The timing to release it for public use. Of course, it's a paid subscription. We're timing to release it during my 51st birthday. That's next month. So in about 10, 11 days, this will be ready for use, right? For learning. And it's so, like I've been telling you, it's a whole, this is a combination of years of work, actually, right? It was only recently accelerated. The last 4 or 5 months, we're able to accelerate the development using AI. In actual fact, this idea, the first note, when I look at all my notes, the first note on this idea was documented in 2011, and then I've been on and off in it. And then the last few years, the accelerated work. So this is the module, right? I will introduce it maybe later, the practical, right? The implementation of a full PLC ladder, right? For PID. It's on the platform also. So in the scenario here, so two things for PID, right? This is an exercise where you construct your own ladder to implement the PID algorithm. A temperature controller, right? And then this is the full rung, right? Where all the explanation, the detail, so you can see from rung 000 up to rung 20, right? You can see all of those, where you do the mode selection, where you do the error calculation, where you do the anti-wind up. Then this is for the D term, the D term, the output sum. Then what we call the bumpless transfer. Then safety, right? So let's see how we'll be able to move. Let's see how fast we'll be able to move. All right. So let's get into it. So introduction, and again, this is an introduction. Why do you need to understand this algorithm? There is no manufacturing plant in the world that does mass production of goods that does some automation, that produces, mass production, that does not use the PID algorithm in one form or the other. So when we did control systems in the university, for those that did electrical electronics, there is the control theory course, right, where we did control systems and we did all those mathematics. The next step after that mathematics is this algorithm, right? This is the what we refer to as the classical control theory. I mean, this is built on the classical control theory, right? All the concept of stability and so on and so forth, right? So, if this algorithm is so popular, why do we have this much level of ignorance on it? This algorithm saves manufacturing plants a lot of money. An expert on this algorithm will make a lot of difference in the plants because you'll be able to tune processes and you'll be able to save energy. You will drive efficiency in the plant. And if you understand this algorithm, other algorithms like ratio control, which is used a lot in manufacturing, cascade control in pumping applications, even feed forward control, they will be piece of cake because you will be able to understand them fully. So that's why it's very important we spend time to understand. And like I always said, if this is your first time interacting with this, you don't sweat it if you don't understand everything fully. When you understand, when a new concept is introduced to you, right, it takes time for your person to be comfortable with that concept. So it takes doing it over and over and over. There are different modes of learning, and that's one of the things we considered while designing the system. You learn by reading, by hearing, by practicing. You touch, and then pictures. You learn by seeing, right? Multimodal learning, right? And the form of learning we call project-based learning, where you plunge into a project and then you wobble and fumble through it. You make mistakes, you correct, you make mistakes, you correct, and then you eventually master it. And that was the thinking behind this product in the sense that for automation projects, we cannot allow you, in fact, if we have not tested you and um, and convinced that you are competent, we won't even put you near the project. Even those that are competent, they are struggling to get on project. So you won't have the chance to wobble and fumble through real projects. But in a simulated environment like this, you can learn all you want to learn and then transfer that knowledge to physical projects. So today, the platform is organized in concept, and then you have the walkthrough, you have the simulation, you have the quiz, and then the summary. So, what we hope you learn, what the PI and D terms do, and when to use each one, how PID eliminates steady state offset while controlling overshoots, how a PLC executes the algorithm in ladder logic, and how to tune a PID controller using a step test based method, right? Of course, there are different types. There are different methods of tuning a controller. And this is one, and which is quite efficient. There's the Ziegler-Nichols method. There's the trial by error method, and there are different methods like that, right? And okay, so over 95% of industrial control loops use PID. And of course, you know that PID is different compared to P and ID, right? Every valve controller, every valve controller on a separator, every governor on a turbine, every temperature loop on a heat exchanger, they all run a PID algorithm. Understanding PID is the single most valuable skill for any process control or automation engineer. We say that school is scam, but just because I understood this algorithm many years ago, I mean, this easily is about 10, 12 years ago, I was able to build a system that I made money. Yeah, of course, I made money from, yeah, because it's money from knowledge. It's not entirely a sophisticated system. In fact, it's for people that wants to dry. They used it to dry brewery waste. There is this waste that comes from breweries, right? And the way they were drying it, they normally spread it on the rock. And I was driving on that's Ibadan to Ife Road, and I saw it, and I got curious. Okay, yeah, it was actually about to rain, and I saw people scrambling, trying to pack this brewery waste, and I was like, interesting. So I started thinking about it, and then I spoke to some people, and then they told me they use that thing to feed the pigs, and that they tried. Someone constructed a system, but it gets burnt. And I just took a sample of it. I took it to the University of Ibadan. I took it to the food technology department or food science department, and then they ran a temperature profile to understand the heat, the point at which that product gets burnt. So I got that range and I set up a temperature control loop for them using that range as my set point. And the system worked. And then, for those that use a machine, well, I actually built it for one person. You know, the woman was able to dry, you know, the brewery waste, and they were able to avoid that scramble whenever it rains. Because if rain falls suddenly, boom, it washes a lot of it away. Because those things are like particles. You know, so that's the importance of this understanding. So in the previous module, M6, you learned how to measure the process time constants. Now you will see that you will use that knowledge to tune the controller that drives the process. And your drives, of course, many of you that works in manufacturing, your VFDs, you know that even in Nigeria alone, we have tens of thousands of VFDs, because everywhere you see an induction motor, you have a VFD somewhere, right? So you have VFDs for induction motors, for DC motors. You have motion controllers, right? Your the drives that controls your conveyor systems, right? So we have all of those. So so and all of those drives, they have the PID algorithm in them. They have the PID algorithm in them. Yeah, some of them even use more advanced algorithms, but most of these other algorithms, they are essentially a modification of this PID algorithm. All right, so let's move. So the equation is U of t equals to Kp, the proportional term, multiplied by the integral time, multiplied by the error, which is a function of time, plus Ki multiplied by the integral time, and then Kd multiplied by the derivative time. Right. Now, let's take a note here, especially for, people in the academics. This DE for KD, in practice, we use PV, and there is a reason for that, right? So instead of differentiating error with respect to time, we differentiate the process variable with respect to time. And that's because KD, that's because of the role of KD, right? And we'll see that as we proceed. But this is the general formula. So when you see the function block from Siemens, the PID function block from Siemens, PID function block from Allen Bradley, from Yokogawa, from Modicon, all of them, 100% are built on this equation you are seeing on the screen, which means that if you master this equation, you've practically mastered 80% of the function block of any of the operators, right? You've mastered 80% of the function block of any of the operators. All the differences are in these terms, right? All the differences, each company will now, they built the function block, they implemented it rather in specific ways. And I always refer to that as marketing. The difference in the function block across these organizations is essentially a function of marketing because, for example, I used to work for Rockwell Automation, and we call our own PIDE, right? PID, enhanced. The E there is enhanced. So we enhance it with additional properties just to separate it from others. Okay, they enhanced it. I'm not part of it, so it's not we anymore. All right. So the terms. So E is SP minus PV, right? Which is the error, and U is the controller output to the valve. Using the valve as an example now, right? So U is the controller output. It could be to the valve, it could be to the pump, it could be to the motor, right? So think of PID as a team of 3 specialists. You have the P that reacts to the current error, a driver steering into the bend. You have the I term that fixes persistent past errors, an engineer recalibrating after drift. So the integral term is not useful for prevention, right? It is only useful after the error has occurred, right? And then we have the derivative term, which anticipates future changes, right? So it's just like saying a co-pilot warning you are turning too fast. So you are driving on a windy road. For me, one of the scariest windy road I've been onto in Nigeria is the road between Jalingo and a place called Gembu in Taraba State. That road, it's in the same state. From Jalingo, which is the capital, to Gembu, it's about 8 hours. I served in that city, and it's like you're climbing up the hill, and it's winding. And the drivers, those commercial drivers, they've mastered that road so much that they speed on that road, but because you are going for the first time, man, someone will nearly have an heart attack because those guys, it's as if they are driving as if the intention, was to just plunge into the road. So as they are taking the turn in speed, imagine a co-pilot behind them, beside them saying, hey, you are driving too fast, and that is the derivative term. The integral term Now look, oh, you turn the steering too fast. So next time, sorry, you turn it too fast. Now reduce it, right? So the integral term will fix past errors, right? It always reacts to the error that already occurred, right? So the integral term tries to take care of your x. If I use, if you permit me to use that term. So while the derivative term anticipates future changes, right? Now the p term, which is KP setting. So these are the properties. The p term is proportional to the current error. So if temperature is 5 degrees below set point, the heater gets 5 times Kp more output. So essentially, it's a straight line graph. For every y, there is a corresponding x. You can describe that equation using y equals to mx plus c. That is the equation of a straight line. It's a direct proportion relationship. So if Kp is too low, you will see the reaction will be sluggish. That is, it takes a long time to respond, right? If it is just right, you'll see fast response with small residual offset. If it is too high, you'll see oscillation. It overcorrects and ons. When we say something ons, it is essentially oscillation, right? So, I mean, we'll demonstrate all of this in the simulation just now, right? Yeah. Okay, I wanted to point out the disadvantage of proportional, the p term. You can use a p term controller only. The disadvantage is that you always have this offset. Always. It never brings your process to set point. You always have the offset rather, right? So there's always that offset, all right? So, and the proportional term in terms of cost is the cheapest to implement. Is the cheapest controller you can implement in terms of cost. So the key limitation is the P only control always leaves a steady state offset, right? The controller needs some error to keep the output non-zero. If temperature reaches SP, error drops to 0, then output drops to 0, and temperature drifts away again. That's very important to note. So for those that that are planning to write certification exams and so on and so forth, this is key, right? Because it's a key characteristics of the proportional controller, right? It leaves a steady state offset. And why does it leave a steady state offset? If they ask you that question, even in interviews, because the controller, the P controller, needs some error, in order to keep the output non-zero. Otherwise, if there is no error, right, then there will be no output from the controller. And once there is no output from the controller, the process will drift. So let's assume that the output from the controller controls a valve that regulates the fuel that goes into the burner, and that fuel maintains the temperature of the process. So if the error becomes 0, then there will be no output, to that valve. That valve will not supply fuel to the burner, and then temperature begins to drift. So your process will not be stable, right? And then But some processes, and this is where your genius is as a control systems engineer, some processes can accommodate what we call the steady state offset, right? I mean, it doesn't have a big effect on it, right? So they can accommodate a steady state offset, and you discover that they will be fine. So you don't need to implement a PI or PID algorithm for those one. An interesting exercise, which I've been thinking of, I've never had time to set it up or implement, will be to set up a temperature control system for frying plantain. Of course, okay, so many of us are here are Nigerians. You know that plantain is a very wonderful food. But if you're frying plantain and you look away for just a few seconds, that golden brown plantain will turn black immediately. So the temperature margin, the margin between the plantain being golden brown and turning to black, right, is very narrow. So we always rely on the person frying how do we call it now? So the person implements a PID algorithm in his mind, in our mind rather. I mean, women do these things a lot, in our mind, and anticipate when the plantain is brown enough. And once it is brown enough, boom, shuts off. Quickly take the plantain you know, out of the hot oil so that it doesn't get brown, and sorry, it doesn't get burnt and turn black. And that would be an interesting, fun project to do, sometime. Combine a vision system and a temperature control system. So let's see how we can minimize the energy, needed to fry plantain. Because number one, your product is plantain. You want it golden brown. That is the most desirable point where you can command the highest amount. Once it is black, you either eat it yourself or you discard it because your customer will not buy it. Right. So that means that the energy you use from golden brown state to black state, you just wasted the energy and then you wasted the product also. And that's a loss. So imagine producing that on a large scale. And that begins to show you the importance of implementing a proper control algorithm for processes. Okay, let's move a bit faster. The integral term, the I term accumulates error over time. Even a small persistent offset will build the integral until the controller eliminates it completely, right? So when integral is 0, offset remains forever. So when your I time is 0, offset remains forever. When it is just right, you eliminate smoothly. When it is too high, you have what we call integral wind up. So the wind up is the overshoot and oscillation, right? And if I quickly run into the PLC simulator, right, you can see where is the where the let's yeah. So look at this rung 7. Can you see my screen? Yeah. So that is where we implement the anti wind up, right? And so you know what the term wind up is now, right? So you can see, you can have the setting can be too low, just right, or too high. Getting the just right setting, and then the just right setting simultaneously, if you're implementing the PID algorithm, I mean the 3 terms now, getting it right at the same time is the genius of the control system engineer, right? And that genius, of course, is driven by understanding and learning, right? So getting it just right, that is when we say that you have tuned the process. If it is too low or too high, if it is zero or too high, same thing, too low or too high, the same thing with the derivative, right? Zero or too high, right? Okay. So if it is, okay, so just a term, okay, I'll come back to that. Now, so for the derivative, the D term measures how fast the error is changing. That is why it is derivative. For those of us that did integral calculus, that did calculus, derivative is essentially the rate of change. When you have a slope on a curved line, the slope changes along the line. The value of the slope changes along the line. And when we measure that, that is the derivative. The rate of change, along that slope. So imagine that road from Jalingo to Gembu that is windy. It is not just windy, but it is also climbing. I mean, so as you are going in a curly manner or curvy manner, you are also going up. So the changes are occurring over 3 dimensions: your X, Y, and Z dimensions, because you are climbing and then you are turning along the X and Y axis, right? So the derivative action measures that winding, right? And it helps you to apply, it warns you ahead. That's okay, slow down, slow down, so that you don't overshoot, right? So the D term measures how fast the error is changing. If error is shrinking quickly, the D term breaks the controller and then reduce overshoot before it happens. So this D term essentially is like a soothsayer or a prophet, someone that sees the future. Of course, it's mathematics, He uses mathematics to look at the future and then apply control, right? So if it's zero, no breaking, you have more overshoot. If it is just right, it damps oscillation, and then your process gets to the set point faster. It settles there faster. And if it is too high, it amplifies sensor noise and your output becomes erratic. So when to use D, processes with large inertia. Large inertia is big tau. Who can tell me what does tau means? Who remembers? Okay.
Time
So
constant.
processes, tau is a time constant, the process time constant, right? So processing with large inertia and fast set point changes. So when to avoid D? When you have noisy measurements, right? Flow or level, derivative amplifies noise, right? So you begin to see that you avoid the derivative term when you have noisy measurements because it amplifies noise. Recall earlier, measurements in the control loop, your measurements, the value of your measurement is the PV, your process variable, right? So the equation says that the derivative term is dE, derivative of error with respect to time. So that's why I said that in actual implementation, we implement the derivative term in terms of the measurement, the PV, because PV, error changes instantaneously. So if, for example, the process is at set point, let's say set point is 50, right? And then there is a disturbance, and then the process went to 80. The value of error will instantaneously become 30. And that 30, that instantaneous I value will D will go crazy. So if you use that value, right? So, but because of the time constant measurement, the history of the process and then the nature of the PV, D already knows the history, right? Because it has been doing that derivative. It has been monitoring that rate of change, so it's easier to use the measurements with D as opposed to using the error, right? So, but when the measurement is noisy, you avoid the derivative term, right? I mean, of course, flow, you know how flow is and level, right? So, using your PID only when you have non-critical loops and when small offset is acceptable, right? An example is your flow ratio split, right? For PI, most loops, I mean, this is the most popular of the configuration, because it eliminates offset without noise, right? So in your level loops, your pressure loops, and so on and so forth, right? The PID is popular with loops with large time constants and tight performance needs. So distillation column temperature. So in breweries, for example, they implement this a lot, right? They implement, the PID, the algorithm a lot, right? So this is the key. So that's why I mentioned earlier that those that have been on the training earlier, even though we've been doing definition of terms, explaining the concepts, but this is where we're using all those concepts. All right. Right. So, yeah. So in practice, 90% of industrial loops use PI. So that's why I mentioned it is the most popular controller setup. And the full PID is reserved for cases where overshoot must be minimized and the measurement is clean. So you can easily see the characteristics when overshoot is minimized and the measurement is clean. That is when you use PID. And you can begin to have intelligent discussions even with this introduction now, because when you are talking about optimizing the plant performance, all right, any control systems engineer that can demonstrably save a plant cost of energy, I mean, that person is going to shine. I mean, of course, you know what energy is like in Nigeria presently, domestically, not to talk of industry. The amount you pay for band A is a chicken feed compared to what the industrial customers pays. So for every watt of electricity you are able to save through your genius, through optimizing the control system in the plant, you are going to get very good commendation, from your plant manager or your CEO. All right. So how PID runs in a PLC. So all of these are mathematics, right? All of these are mathematics. How many people write, if you write code, if you're familiar with, if you write code, whether using C or Python, can you just give me a thumbs up here? Okay. Okay. Interesting. Nice. Nice. So you can see that there are, I mean, maybe later I can recommend projects that you can do in order for you to practice tuning in your house using your Arduino or Raspberry Pi or any of those development boards, because you can write a Python code, or there is a discretized function, format for this equation, right? The Python program or C, and then you can use this to control a motor. You can use it to control a motor. You can create like a lift, what you call elevator. Yeah, you can use it to control the elevator, and you can use it in some hobby electronics projects, right? And it will illustrate to you in a much more deeper way the implementation of this. So in the industry, so in industrial practice, PID doesn't run as a continuous equation. Yeah, exactly. So it runs inside the PLC as a function block that is called every scan cycle, right? Typically 100 millisecond. So the PID function block in ladder logic. So this is how it looks like. So you take your, so this is the block, right? All of this, okay, so this is the block. This is the PID enable. So the way it is implemented, so I need to move between this and this now. So the way it is implemented is you have your block on your ladder logic, right? You now need to set the mode, your mode of operation. Are you on manual or auto? So that's where that term comes from. When you are on auto, the operator is not doing anything. The system is, doing that, right? Is carrying out and the activity. So that is manual auto. Let me quickly. What's the time now? Okay, so yeah, okay. Let me quickly illustrate that. Uh, mm, okay, so that okay. Don't let me waste time here. So, by the way, thanks to those that registered for the field course, right? We're having our um, what's it called now? Induction this morning, right? And we'll delve deeper into all this. We'll have time to dig deeper into all these concepts, right? So, you move from manual. I think we'll even see it in the simulation here. Uh, so you move from manual to auto, right? These are the parameters. So you can see your PV, your SP. This is your output. This is actually your MV, right? This is your KP, the proportional term. So you set it as 2, the KI as 0.08, and then KD as 0.0. So in this instance now, they are just using the PI. They are implementing the PI control, right? Because they set KD to 0. If you look here, when you set KD to 0, no braking, so more overshoots, right? So, but you have determined as a control systems engineer that you don't need KD for this process. Probably this is not a temperature loop, right? And then this is where you set your mode, auto or manual. So this is what you tie to the HMI, right? So you tie this to the HMI, and then you have your, you can select whether you want the algorithm to run the process or you as the operator, you want to run the process. There is a very small simulator in one of those courses, but because of the time, I have a hard stop in 25 minutes. So, I mean, you will see the difference graphically between the auto and manual. So what happens each scan? You read the PV, you calculate your error, you implement your P term, the I term, the D term, then you sum, and then you clamp. That is, you limit your output, right? Limited to 0 to 100% or as calculated, and then you write output. So you, whatever value you arrive at, you send it out through your analog output card, as a 4 to 20 milliamp signal to the valve, right? And then there is a term we call the bumpless transfer. That is the transition between manual and auto, right? So when switching from manual to auto, the integral is preloaded to match the current manual output. This prevents uh, a sudden valve jump, right? And all of these concepts are so I mean, pardon me, but because I'm excited about this system, I mean, this concept, so this separator simulator is a very, 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 so it's a system lesson, right? And it essentially model the oil production from wellhead into separation into its components and all the different control systems and algorithm involved. So the process overview, the normal operation, the pressure control, the level control, the trips and shutdown, the diagnostics, troubleshooting sensor drift, the stop valve, and then your ESD latch, yes, in the PLC, your eye level interlock, and your dual protection system, and then bad PID tuning. So this is a case study that shows all this theory, it's implemented, so if you left your loop left in manual, right, the oil level controller was left in manual after maintenance, level drifts uncorrected, diagnose and return to auto, right? It's like I mean, it's an activity that will task your brain. And then this one is PLC not latched, and then maintenance bypass. This is a very comprehensive case study, patterned after an actual industrial process, and so many of those case studies are coming up and will be on the platform. So you have Yeah. So you do all of those, and then your bumplex transfer. This is a very important term, in the DCS environment, right? Uh, if you want to impress people, I mean, they will use these terms a lot. So they will know that you are among, so to speak. If you understand these terms, right? And then we talk about direct versus reverse acting. I'm trying to move fast now so that, but probably we'll still come back to this maybe next Saturday. I'm trying to, I want to get this going every Saturday, just do 90 minutes and take that learning quickly, and then we can get on with our day. All right. Direct versus reverse acting. This is a very, very important concept, which actually will take a lot of time to explain. I know that we've discussed this sometime many months back, I think last year, where, we discussed it on the chat group, where I think someone asked a question, and then I now asked some questions to answer those questions. And that's, what's the relationship between direct acting, reverse acting? In valves now, you have what you call FO and FC, that is fail open or fail close. And then in electronics, you have normally close, normally open. All of these things are similar concepts that you need to be able to resolve. They are not entirely intuitive, but you need to be used to their thinking, because these are the things you will encounter in the plants, right? So direct versus reverse acting. So we have direct acting controller and we have reverse acting. So um, so for those that attended the last lectures, we said that error is SP minus PV. That is when we are talking about direct acting. But reverse acting, error will be PV minus SP. Right. So we need to have that. So you can begin to see the nuances in all of this. But I mean, this is an introductory class, right? So when output increases for direct acting, PV drops below SP, valve open. For here, PV rises above SP, and then valve opens also, So you can see the concept, right? So, okay, so this is illustrated on the separator case study, the separator process. All right. Then how to tune. So you use your process gain and time constant, right? With your step test. So you measure K and your time constant. There is a way you measure it, right? You put the controller in manual, you apply a 10% step, and then you record the response, and then you calculate the initial gains. So that's a lambda method, right? And then you have your KP using this equation, and then you have, so for PICDs now, right? This example is taken from the separator process, right? And then you have this value. So this value for KP, this value for KI, right? And then that is what you will now put inside your program. So your KP will now be that value, your KI will now be that value. Please give me a thumbs up if this is making sense. At least making sense. I mean, you might not have the 100% understanding now, but let me know if the foundation is being built. Okay. All right. Okay, someone does not understand. Do you have, okay, so what's the challenge? Can you quickly open your mic? and tell me where is the source of confusion, or you drop a comment in the um in the chat. Okay. So you can drop a comment if you don't. Okay, tuning. So tuning essentially is okay. Just hold that thought. Hold that thought. We still have about 15 minutes. Let me move. Let's get to this simulation at least before we leave. We'll see all of that. I mean, so this is mathematics, right? And so this is the calculation you do, right, to arrive at the values you set in here, right? There are softwares now. One of the most popular companies that does tuning. So there's this company called Control Station. Control Station. Yeah, this company, controlstation.com. You can subscribe to them. I've had a training with them in the past, right? And then they have a newsletter. And the only thing they do, the whole of this company, they build software for tuning processes, and so they have. I mean, you can see the caliber of industries they work with. Okay, all right. So common mistakes. You test and then you fine tune. So the step is this: you measure your K, that is your process gain, and then you understand your tau, the process lag, right? And then you calculate your initial gains using the lambda method, and then you test and fine tune. So too slow, long settling, increase KP, by 20%, increase KI by 10%, oscillating, reduce by 30%, offset, reduce, overshoot on disturbance, add KD 0.5 times style times. And those are guidance on the values you use, right? And these are the common mistake. So we'll try it in L3, right? So let me mark this and come. So in summary, this is a summary. P reacts to the current error, I accumulates past error, D breaks on rates of change. And then most industrial loops uses P high. In a PLC, PID runs as a function block that is called every scan cycle. Yeah, I was going to mention, right? So when you write your PID and you implement, when you write your ladder logic and you implement this PID function block, you need to pay attention to your scan time, all right, the scan cycle, because it's going to have an impact. And so we spoke about the bumpless transfer, the direct acting, reverse acting, and then auto tune, right? So let me move to the next one. So I'll just gloss through this, right? This is just the instruction actually for the simulation here. So I want us to spend the remaining 10 minutes on the simulation, right? So that I'll introduce that and then we'll continue next week, Saturday. All right. I can print this out and just how I'll print out these sections, right, and drop in the group so that you can look at it against next week. We'll come back to this PID next week. Yeah. So this is a simulator, right? These are the parameters, right? So you have your proportional gain, is direct and reverse something set once per process or calculated. No, it's set once. Once you configure your process, right? I mean, it is set once. It is not, or is it set once or calculated once, or can it be automatically changed? I thought the controller can adjust for positive and negative values of errors. Without this, there will be no oscillation. But with this, it looks like the error has to be positive always. So these are two different things, right? How do I explain this now? So these are two different things. Direct acting controllers, reverse acting controllers, they are just what they are, right? You need to, so if you are using a direct acting controller with, you need to have that mindset when you're using a direct acting controller with a valve, for example, that is either fail close or fail open. All right, those actions determines what the valve will do in the event of failure. So for some valves now, for some controllers, a direct acting controller, the minimum value it's going to give you will be 4 milliamp. The maximum value will be 20 milliamp. For a fail open controller, right? The minimum for a fail close rather, the maximum will be 20 milliamp and the minimum will be 4, right? So you need to match the output from the controller to the movement, to the design of the valve, right? For you to understand this relationship clearly, you need to understand how, you first need to learn how valve responds. I mean, the configuration of valves. How are they open or closed? I think I've done that explanation some time ago. The bonnet design determines whether it's going to be fail open or fail close, right? You can supply here from the top or from the bottom of the bonnet. The point at which you supply that air determines whether it's going to be fail open or fail close. But drop this question in the chat group and let's brainstorm on it. Let me quickly spend time on this simulator here. All right. So we have, these are the PID parameters, right? The KP, KI, and KD. The temperature, the process temperature is 20 degrees Celsius. That's the PV. The error presently is 40, right? Because SP minus PV is this. The output presently is MV. And then, all of this. And this is the time, right? So let me just use the speed at 5x so that it runs us through. Let's start with, let's shut everything down, right? And then if I click start, you can see this is the process parameter. So we have, in this process now, the condition is that if there is temperature deviation, if it exceeds 25 degrees for 20 seconds, right, the process should trip, right? So that's exactly why we have this process trip, right? Right. Good morning. Yeah, so that's why we have this process trip. So we need to acknowledge and reset, right? And then if I move this to, let me just put it at 2. So let me keep this at 2. Now, 5x also, let me start. So you can see the process did not get to within that range, within the time, right? So we have that also, right? Now, let me introduce the integral term, right? Or let's do this. Let's increase this again, right? So that's the temperature rising. So at 3.6, we have it. So this is a controller output under, right? And then you can begin to see that at the P only value, K high and KD are 0, right? We have this offset, this sustained offset. The process is still running, but the offset is there, right? So that is the impact of, that is how P behaves. This is the SP. SP is at 60 degrees Celsius. And then you have this, right? So you can see temperature is 42.9, even though set point is 60, right? So we have an error of 17.1 degree Celsius, right? Let me say that wrong, right? Now, let me introduce an integral value. Let me just make it 0.18, right? Next week, we will use the rule defined in the walkthrough to do all of this, but I just want to show you this concept so that I don't leave you hanging um, before we finish, right? So we are still, KD is still 0, right? Let's start. So now look at, you can see that the output MV goes to, pushes it to the maximum. Now the integral takes it, it goes above, now it drops. Can you see the oscillation? Right, it goes above, right? And then it tries to settle in, right? So you can see the derivative, right? And then it's approximately, right? So it brings it to the set point, right? So let me reset. Let me clear this, right? Now, let me add, okay, let me increase this. I want us to see that oscillation. So observe the process variable. So it goes above the process, that overshoots, then it drops, then goes above, right? And it drops. Right. So it eventually settles at the set point. All right. So the PI controller will eventually bring the process, to set points. Right. Let me say this one. Right. Now, let me introduce the derivative. Right. Now, start. So you can see the output is oscillating between 99 and 100. This takes it, as it is approaching this, derivative will calculate the overshoots, right? And then slows it down, right? And then it oscillates a bit across the set points, right? And it settles there. So the rate of change, that is what the derivative parameter, the rate of change, right? That's what the derivative parameter introduces, right? It's the parameter brings your process to set point faster. So the integral will eventually bring it to set point or to stability also, but it takes more time. The derivative reduces the time to attain steady state. Do you understand the difference between the function of the integral and the derivative terms? Right. So the proportional term will give us a steady state offset. The integral the integral will bring the process to stability or to set point, but with some oscillation. It takes it up and down, and then eventually settles, right? And then the derivative, the rate of stability, the rate of attaining stability, the derivative makes it faster. So, yeah, I hope that makes sense to you. The next thing here, we're supposed to, okay, we need to do, or okay, we need to answer these questions. And then, what does derivative action do, right? Select the best of description of derivative action in a PID. D responds to the current error, just like P, but scale differently. Let's quickly answer this, if you can tell me. D measures the rate of change of error, breaking the controller before it overshoots. D eliminates steady state offset by accumulating error over time. D makes controller ignore disturbances and only respond to set point changes. What's the answer?
B.
B.
Yes, B.
Okay. So that's correct, right? So add derivative, yeah. So that's okay. So that's that will be it for today, right? That will be it for today. If you have any question, please drop it in the chat group and let's continue the discussion there, right? No, what will I say now? There's no question that is foolish, right? So these concepts are abstract, but they are very, very important concepts to understand as you grow in your career. So don't be shy in dropping your questions there. And I mean, it might take me a bit of time to respond. I monitor the chat group often, so I will respond to it, and we can all debate and come to a conclusion on it. So next week we will continue. We will start from here. I'll do a review of this. We'll finish it, right? We'll finish this module and then get onto the alarms and safety basics, where we'll talk about the alarm hierarchy, the I alarm, the II alarm. We'll talk about permissives, interlocks, latched trips, right? And then practice the complete, all the posted reset procedure on a live tank level. So yeah, I mean, so we'll continue with M7 and finish it, and then at least start with M8 until we finish this series. So I think we have 2 more classes in this series before we move to other things. So thank you very much. I'll need to step out now. Like I said, always talk about your experience. Whatever you can Google. I mean, the things you don't understand, you can just Google about it and read. And then what's not clear, you can always drop the question in the chat group. Thank you and have a beautiful weekend. All right.